Want to see how to send your own hardware to space? I'm doing just that with Hunity, a tiny satellite launching in just a few weeks. But time is tight and there's lots to do. Last time, we talked about the mission and designed it. Short version, we got a tiny spot aboard a tiny satellite, so I had to squish this amount of functionality into this amount of space. Did that, and we wound up with this. Oh yeah! Designing is the dream. This is where reality hits. Mistakes lurk, bugs bite, and deadlines loom. But that's what makes this thrilling, right? Join me as we battle through assembly, debugging, and programming to create a space-ready experiment module. It's going to get messy. Can we make it work before launch? Let's find out. The very first thing we need to know is if these things work at all. I have to get a few assembled and bring them up. So I got the workbench tidied up and got down to it. I got warmed up with something easy, these little program debug boards that let you interface with the modules through USB. So starting with these guys, the program debug external things, because they're low pressure and just easy to do. Only a few to do, so I place the components by hand. Though you might not care about the precise value of some pull-up resistor, I always double-check anything critical, like the USB-CC line pull-downs, before populating them. 1K? Yes. Okay, USB's going to be happy. One of the uncertainties in the design was that rather than being smart and using pogo pads or some JST connector I already trust, during design I kind of had a brain fart and put in a Molex connector I've never used before just because it was tiny and had a low profile. Can move this tiny thing a lot closer to the RP2, which is good for the USB lines. Still, like I said, I don't know these, but who doesn't love to live dangerously, eh? And we only have one chance with these boards, so that was a bit dumb. Yeah, these are the ones I'm still not sure about. Anyway, stuck them on there. I didn't bother with the reflow oven and just used a hot plate to cook them. And that was that for these simple PCBs. Great. Okay, enough prevaricating. Now the scary bit. Will the experiment modules actually work? Since I didn't know if some giant mistake was lurking in the design, I didn't want to commit all the precious ASICs or my precious time to assembling a bunch. The hardware is tricky though. Design may be fine, but you still have issues with the assembly itself. So I decided to increase my odds and do 3 in the first go. I went and prepped all my parts and set up the stencil to paste. Now that wasn't the best setup, but it did the job. Then I went through and got everything stuffed on the 3 boards and cooked them up to wind up with 5 program debug PCBs and 3 fully populated modules. After making sure there weren't any shorts, the first question was, can I actually talk to the microcontroller from USB through the programmer board? I was too stressed about all that to even remember to film the process, but here's how it went. Oh yeah! Oh, phew. So at a minimum, I'd be able to interact with the RP2040 chip. First hurdle cleared. Phew. I confirmed that by installing the standard PyPico micropython on the chip and then connected to the REPL. Wow. Okay, that's a good start. Now 3 really fat open questions are looming. Do the boards work, like completely? Do the microcontrollers good? Yeah, but what about the ASIC? Will we be able to do all the things we want to do, like running user experiments? And will we even be able to talk to the satellite? Now to answer each of these, we need software. I had a grand plan about working on the software while the PCBs were being fabricated. It was a good plan. Now, though I'd love to say something like, life got in the way, but the reality is that with the uncertainties in the whole thing, the fact that I only had one shot and everybody's hopes of running code in space was riding on it, well, I kind of froze up for a little while and hadn't done any software at all. It happens to me anyway. With maybe working boards in hand, the only way to know if it's going to work involves coding. Now, the bit over which I have the least control and knowledge is the third question. Can we even talk to the satellite? If not, it's not even worth doing the rest. Now here's the problem. The satellite expects all the experiment modules like ours to be on an I2C bus and respond to its reads and writes, i.e. to be a slave device that reacts to the satellite's commands. I've got 2 suitable pins routed out just for that purpose, and the RP2040 supports all this. Great. But our code for the ASIC and the tests people will be writing to play with designs, that's all in Python. And MicroPython doesn't support I2C slave mode yet. I rolled up my sleeves and got down and dirty crafting a custom version of MicroPython that would support this. It took some work, but MicroPython makes it easy to customize. If you want to deep dive into that, let me know. Short version is that I broke out a Pico and went to Code Town. Things seemed to go well. Check this out. Okay, so I've got
two devices connected on this messy desk here, and so they look like that. And what I've got here is one is the demo board, which has no chip on it, but it's just an RP2 there, so that's good as my master device. I now have an I2C slave library running on that other little module, so I can write to it. So hello, this is a very nice test. Boop. Now I just sent 30 bytes. And on the slave, there you go. Hello, this is a very nice test. I could also basically, if I come in here and I go I2C queue up the data, ha ha ha, ho ho ho, whatever, whatever. Okay, now that's queued. Now I'll queue some other stuff. 1, 2, 3, 4. Okay, so now I've sent 2 bunches of bytes to be queued, and of course the slave side doesn't know anything about this, but if I read from there, I get the first bunch. There I get the rest of the next bunch, because that was more than 16 bytes, and the final little bit. And here we go. Is the second string that was in there? Yes. All right. If you read over the edge here, it's just sending OXFFFFFF. So how that's working, so I started by looking at the examples, the slave mem I2C stuff here, and it's nice, but it is the CSDK. Yeah, so that's great, CSDK, but all our tests are going to be written in Python. We need to be running Python. So what I ended up doing is this. Now, this is middleware for MicroPython, and I won't bore you with the details. It was something to write, but in essence, what I'm doing is I'm setting up a bunch of, let's go down here. I'm setting up a bunch of these basically functions that I'm exposing. And so what I can do is go on the slave side and say I2C slave, and you can see these functions here, initialize, set up, write bytes, read bytes, whatever, that is coming from here. So that's on the MicroPython side, and I had to recompile MicroPython, which was actually pretty easy. It's not that bad. So that is basically all these functions here, which are using these guys here, which were inspired by that example from the Pico stuff that uses the CSDK. And then I've got basically a little class that I created on the Python side to represent the device and deal with the queued buffer. Anyways, I'm going to push this to a fork of MicroPython. But for now, the important thing is I2C slave working in Python, so I can get back to Python and get to implementing what we need for the for our driver for the satellite. So yeah, getting kind of late, but I can't resist. I'm going to do a little bit more.
So that was very promising. I'd nailed down the low-level I2C and answered the first question. Yes, we can talk to the satellite. Now I could get down to coding Python. I built up a whole system, an API and protocol to launch and monitor experiments, a client-side simulator to actually use that protocol to control the device over I2C and interpret the responses, a system to load and run experiment modules, all that stuff. It was fantastic. But then, something weird. What? My code wasn't trying to call a list. Anyway, worse was that it would happen randomly. The object in question would change to other types, string or whatever, and this exception wasn't actually being caught by anything I controlled. It was happening somewhere weird, in a thread or something, and stacks were being smashed or pointers were dangling because somehow memory was being corrupted. Oh no. At the start of all this, Matt had advised me, try to keep it simple, Pat. Well, I hadn't followed the KISS principle. I had a beautiful system with the I2C driver running on one core, the request handling and experiment runner on the other core, and communication between both sides using command and response queues, passing around objects. It was pretty, and pretty complicated. That wasn't going to help debugging this kind of thing. I spent a long time on this, reached out to the Tiny Tapeout community on the Discord, got some good feedback from a few people like Mike Bell. Troy Byrne even braved getting the whole thing running, doing a cleaned up version of the low-level C module, and still, he also bumped against the problem. I tried a million things and finally slashed the entire codebase down, keeping only the essentials. I completely munged the nifty asynchronous API in the I2C module and just went with polling.
After days of debugging like crazy, I think I may have something that's working. Check this out. That is the demo board, and it's acting like the master on this bus here. And this guy is basically just a Pico that is acting as the ASIC, spASIC. So there you see the lights blinking there. We just started an experiment, and look at that. It's running. So where are the pings? We're at 239 pings and no failures. So that is the slave side. So it's just doing its thing. You saw that green text that was launching the tiny tape out stuff. And so it's running this experiment. And on the master side, we're just randomly doing stuff, launching experiments. Sometimes it's already running, so it reports an error. Here's a completed, so that's an experiment that was done. And it looks like after all of this, it might be working.
Yeah, the problem, a mystery to this day, was somewhere in the interrupt handling, and even though I'd spent a ton of effort working to make them safe, it didn't work out. But polling?
Well, this is exciting. So it's the next morning. The stress test has been running all night, and it's still alive. Check this out.
So this is the stress test going on these boards. So right now it just launched an experiment. You can see that light going. And so it's basically run about 1,500 loops. It's pinged it, 7,793 times. And it's just still running.
It's behaving. That was insane. But now we can get back to business. Cool.
Oi. Okay, tougher than I'd hoped, but we can finally check that box. On to the next. There was still some uncertainty about the hardware. Though the circuit is simple, the only way to be sure is to get it working. Now, the Pico is great for doing I2C dev, but for checking all the ASIC stuff, we need to be on the actual experiment board.
Okay, so thrilled about these little program debug adapter connector things is what I'm not.
They actually work, and I'm going to try this out. Hey, look at that. It's holding. Wow. Amazing. Except that, not so much. That's not wonderful. Now, what I'm going to do is make sure that it actually works for reals, and we can see the device through USB. And then what I'm going to try to do is basically, this is going to be a debug version. I'm not going to send this one into space. I'm going to just stick it together and make it so that I can debug and do different things with this module in a reliable way. Boop, micropython board in FS mode. So that's good. Now if I can just hold it like this, that'll work. So these have little pinholes here for the I2C, and the idea was to be able to have it plugged in and, in theory, debug. So what I'm going to do is try to get these 3 pins connected to those guys on the satellite board, and when that's done, I'll just solder them together, and that way I'll have both a solid connection and maybe a way to, act as the master and do a full simulation. So it'll be like a 2-for-1. The module will hold together, and I'll be able to use the simulator code and go over the I2C bus and control the device. So a nice dev loop where the USB is giving me some feedback on one side and I can update the programs, and on the other side I can actually talk through I2C at the same time just by using some jumpers. It should be simple. Oh yeah, let's go. Yeah. Pretty awful, but gobs of solder should fix it. This guy's blocking it. Metal in your way? Just bend it. Oh, my finger's on the other side. Smirk. What's a little burnt flesh? Am I still connected? Yes. Yes! All right, so look at that. Okay, something I can just plug in, and it should work. Boop. Up here. Yeah. So you can see that the connection is very nice and solid. And actually what I've got in there is 3v3s coming in, SCL and SDA. So what I can do is talk to the RP2 through USB. That goes through here, goes through the little connector, talks to the RP2. And since the I2C connectors are on the sides here, well, I've got these jumpers basically that are now connected to the things that are acting as mechanical supports.
but are also the I2C line. So if I want to test the satellite simulator, the master of the bus, then that'll work too. So this is cool. This is going to make dev a lot easier. Nice.
With that in hand, I hacked up a version of the Tiny Tape-Out demo board SDK to account for the changes on the module, basically the multiplexer we had put in last time. Got that all installed on the dev module and gave it a spin.
So that is cool. So that means I managed to select the factory test. I managed to interact with the outputs. I'm going to check the BIDIRs and all the pins, but in essence, that means that the ASIC works. I mean, we can talk to it. I think we're all set. All we have to do now is like make experiments. I need to make the boards that are left over, but I think it's going to work. Maybe we get to go to space.
Okay, this is going to work. So now we need all the PCBs done. I didn't like the experience pasting the thin boards the first time. It was clunky and fidgety. So a little jig I created with OpenSCAD should help with that. So I got Old Faithful to print her up.
Oh yeah, what a beauty. Very flat.
I did the thing, cleaning and pasting and prepping and placing and placing and placing. I used the hot plate again, but this time to make absolutely sure everything flowed and there were no solder balls left intact anywhere at all. I actually heated from both sides and inspected everything along the way. During initial bring-up tests, I don't trust anything, so I use the power supply with a low current limit and just feed the USB from there.
So I'm going through them one by one and I'm checking the clickiness of the connector, how well it holds, making sure that it doesn't, there's no short or anything like that through the 5V, and finally doing a little bit of check, just a sanity check that I'm getting 3.3 volts here and then I'm getting some oscillation here. So that's the RP2 oscillator. So this one, number 5, is looking good.
So I went through all of those, checking electrics and the behavior of the Molex connectors. Okay, great, but all that tells us is that power and USB to the RP2040 are good. There are like 30 connections between the RP2 and the ASIC, some of them going through the mux, and they all need to be good. To check that, I wrote a little power on self-test that would use the factory test design on the ASIC, and if that passes, then we know that every single connection is good. So I built a version of MicroPython with the latest code and that post and tried it out on all the boards. The good news, some of them came out of the gate like this.
Board 7, copy that, copy done, all right. Well, counter test looks okay. Let's hope the bidirectionals work too. Ah, this is looking good. Okay, we have a board that actually just works.
Others not so great.
Mismatch on the BIDIRs. Oh, but interesting. Okay, it looks like one pin. Let's take a screenshot of that.
But the type of errors coming out did give a clue of what might be going on.
Yeah, so it looks like we have at least 2 BIDIR bits that are messed up on this board.
What ensued is a lot of touching up on a couple of boards.
Okay, on board 1, these guys look really starved, so I'm going to give them some extra. Just a little bit. Boop. A little bit for you. Boop. A little bit for you. Boop. You were there. And you were there.
Followed by retesting until...
BIDIRs looking promising. Total failures, 0. Boom.
Okay, awesome. Boards really do work, ASIC and all.
The champions. These guys actually work. So all those checks. Finally reworked everything, and they all pass everything. Beautiful.
From those, I took a close look to see which ones seemed most solid, clean, and just beautiful.
These are the champions. All right, 4 and 6 selected and going to T-Ball.
Time to package up.
Ready to ship. Ready to ship. 1 SPASICs module. 1 backup SPASICs module. 1 program debug header. Gonna ship this right now. Oh, I ain't messing around. Gaffer tape for the win.
Drop that off. Yay! With 1 whole minute to spare on the last day I could send to meet our extended deadline. Success! Right? Well, no, not quite. A final unhappy surprise was waiting in the wings to bite me. Before I show you, if you enjoy this sort of down in the trenches electronics content, please subscribe or share the video with someone you think would like it too. The channel growing lets me know it's worth putting the time into documenting these adventures. Thanks. So, the last surprise. With the box on its way, it was my opportunity to finish up the code so we could get user experiments and prep a finished UF2 for everything for a final update over there. So I'm doing dev with the demo board, acting as a satellite, talking to my module over the I2C lines. And there's a problem. A problem and a mystery.
Okay, so I'm trying to debug on the actual modules, and I'm getting a lot of these annoying errors. So yeah, it's responding sometimes, sometimes not. EIO means it didn't find the device. And so what I'm seeing is, so this is the module with the connected debug board, and this is my client. So it's connected over the I2C lines into there, and then that goes over the little bridge over the side there into the RP2040. Great. So what happens when I do a little ping, boop, boop, I get some data. That's good. So what I'm monitoring here is the SDA line. So you can see what I'm noticing here is that it goes from 0 to 3v3 and life is grand. But if I switch this and instead monitor the clock, so now I'm going to do another transaction here. Look at that. So there's a lot more clock pulses, which is normal. But the point is, it's not making it to 0. Why would that be? Well, I believe that my connection back there, these guys, these castellated edges here, they're really tiny. And I didn't maybe do a bang-up job actually connecting it. I was concerned about mechanical stability, but didn't really think. So I've got these big blobs here, but I think there's resistance, in short. So I've got some voltage divider kind of action going on. It doesn't seem that way, but I can't explain what else it might be. Why wouldn't SCL make it all the way to ground? Why is that? Let's find out.
Well, continuity resistance testing said no. The problem was not the edge connection. That was fine.
Yeah. Okay, so that's not what this is about. Just not it.
I eliminated the variable of the client side.
Okay, just to make sure my client isn't the problem, these are just fat resistors. Just going to ping. So the SDA line goes from 0 to ground. That's good. And the SCL line, which is the problematic one, also does.
All on its own, the demo board master was behaving nicely on the line. More digging and thinking needed here.
Here I am trying to do my pings, and I'm getting this weird stuff. Now here's the thing. If I change the MUX line value, which has nothing to do with SCL, the I2C stuff, I'm getting timed out instead. Now watch me change this MUX line value back to 1. This scope thing is on the SCL. So change it. Oh no, why am I seeing stuff on SCL? I'm looking at SCL. Well, check it out. Here's the SCL line. Here's that MUX control line. Eeks. Okay, well, this is probably just a solder joint or something on this module, but I hadn't detected anything like this before, so I don't know. I hope what I sent is okay. And this is the MUX select pin. Oh, look at that. How wonderful.
Okay, confirm. That thing is shorted. Damn. All right, a bit of rework and...
Okay, so the SDA is as before between 3v3 and ground. SCL, 3v3 and ground. And here, my friends, is the pudding where we host all the proof. Ping, 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 ping. Ha ha ha. Yes. So we have reliable connectivity. The experiments are running. All the stuff is running. This is
Wonderful. Okay, I'm just hoping now that, yeah, the same problem doesn't affect any of the boards I sent over.
So, wow. In the crunch of crazy debug and the race to meet the ship date, the plan for a decent test plan went out the window, and the inevitable result resulted. Something just a tiny bit fundamental, communication from the satellite to the board, wasn't actually fully verified on the PCBs I'd sent out. Just wow, good job. In a bit of a panic, I tested 3 other boards for the same fault. No, none of them shared the issue. So a 75% likelihood of an OK board in his hands with 2 turns of bat. Not good enough. So I went through another selection round, this time testing everything, and sent that off too. In a way, it's good. This is a secondary option in case anything happened to the shipment itself, and I used the opportunity to send a second programming board, which I really should have done the first time anyway. What an adventure. Now, while those are on the way, I polished up the API and protocol, documented all that, and went for the stretch goal of supporting the file system management and updates. Though I'm trying to get everything right the first time with the software, having the ability to apply fixes while we're up there might just save our butts. So now it's all about the experiments. We already have a few that are known to be working, so it looks like we can check that final box, maybe. And we've got until the end of this month, that's May 2025, to get all the test code for the experiments before the final firmware update. This is where you can contribute. I highly encourage you to give it a shot if you have a design on the Tiny Tape-Out 6 chip, but even if you don't have anything on the ASIC, you can have a look at the designs that are on there and write a little bit of Python code to load one up and play with it, and then get to say that you've had your software running in space. How cool is that? I've fully documented the process, and it's all of 4 pretty easy steps. Check the descriptions for the link for that. Thanks a ton to you who made it all the way through the adventure. I've decided to put out more videos on the electronics craziness I get through, so subscribe if you haven't already, and I'll see you soon. Thanks again. Cheers.